Hello, welcome to Numerical Ship and Offshore Hydrodynamics. Today we have lecture 41. So, this is the concept we are going to cover today. It is continuation of the basic mathematical formulation that we have done for last few classes. Today we are also going to discuss about the numerical modeling. Okay? And these are the keywords that we are going to use to get this lecture. Okay? So, now in last class we discussed that to get the total fluid scalar force over the body, what we are going to do is as follows. We take a shape, and then we have done the cross section, and each cross section if I take the sectional fluid scalar force which is written by the small f. Okay. So, let us take small f I is the sectional force, and then if you integrate this sectional force over the line, that means over the length, we can get the total fluid scalar force. Right. Now, again here we have, now you know that we have 6 mode, right, and in last class we have discussed this f 1 is always 0. So, therefore, we need to take the sectional force only in 3 mode. So, what are the 3 modes? The first mode is f 2 which is sway, then f 3 which is heave, and f 4 which is roll. Now, if I know f 2, f 3 and f 4, so definitely I can get this f 5 by taking the moment multiply the heave mode. And if you get this for the 6th mode, it is nothing but f 6 is nothing but x into multiplied by the second mode f 2. So, this is how actually we are going to get the total fluid scalar force over the body, right. Now, here we are going to check that how we can get the sectional force. Now, in sectional force you know that it is force is nothing but the integration of the pressure. Now, where are I going to do the integration? Now, here this f, since it is f is in the yz plane, because I am drawing the cross section. So, it is with respect to the, it is the y direction, this is the z direction, and this is your curve. So, we can call this is C or C 0. Why 0? 0 is basically I am integrating upon the mean weighted surface. If I want to do for exact weighted surface, in that case it should be C B. So, let us not go into that, let us restrict our attention into the linear case. And then also we know that if I look this previous thing, that it is harmonic, psi is harmonic multiply with e to the power I omega t. Now, if I do that here, this pressure, then it is nothing but minus rho, right, into del, in that case here if I go here, it is del phi I del t. So, here, so del phi I del t. Now, again this phi I, let us take that sectional phi I, which is, let us take vector y, z and t, it is nothing but psi y z into e to the power I omega t, right. So, if I do that, apply over here, then pressure is coming is minus I into omega multiply nothing but the psi into y into z. Now, if I want to integrate it, so get this normal. So, if I try to find out that, so it is, let us say this pressure integrated in the sway mode or surge mode, whatever. Now, if you integrate, then we get this, let us take the sectional force in the ith mode, it is nothing but this integration. So, I just make minus rho over here, minus rho this, and it should be multiplied by that type normal and over this d c or d c 0, or here I am creating d xi. So, that is how we are going to get the force. Now, here you can see I just leave this part, I did not write minus over here. Why? Because sometimes instead of e to the power I omega t, many people take e to the power minus I omega t. If you take e to the power minus I omega t, then this become plus, because this minus will cancelled out. So, therefore, based on the situation it should be minus or it should be plus. If you take e to the power I omega t, definitely you have a minus over there, and if you take e to the power plus omega t, definitely you have the plus over there. And now this is very simple for you for numerical calculation, because this psi is an analytic function. If I go back, I can see this psi is an analytic function. Now, so what we need to do is I need to take the section over here, and then I need to divide this number of panel, and then you need to take the center point of this. Now, in this case panel is nothing but a straight line, because a 2-dimensional curve, and I take the center of this point, and in this center of this point I calculate this numerical value, right, and then I multiply by the normal at this particular point. So, which is here, and then I sum up everything. So, these things essentially this f I equal to, now I just use minus I omega because I am taking e to the power I omega t. It should be sum of is I equal to 1 to the number of straight line. So, I think I have some n number of straight line. So, then I just put this functional value at the middle point of this each section. So, I can just call y m comma z m, and of course, it is I. So, it is basically the middle point between I and I plus 1 in this section, taking the middle point. I just find out the value of psi over there, right, and then I multiply this by that. Now, in which mode, let us say it is in, now I should not use I here because I already use I. So, let us say in the kth mode. So, it is basically for the kth mode for the ith segment. So, this is how we are numerically we are getting the exciting force. It is similar, right. We have done this for before also we have done for panel method, then Waumit type solution also. So, we are aware of how to do this. Earlier we have done it for the surface. Now, here it is even more easier, because now surface requires panel, but curves requires collection of the straight line. We are coming, we are maybe later on if we get time we will show that numerically how could we do this, but right now let us leave this point, because we know how to calculate the Fruit-Kessler force. Most interesting or more interesting or more complex thing is how I get the diffraction force. Now, in case of a diffraction force, there, as I said, there are lot of theories are available, but we are really not going into the theories. Now, maybe in the next lecture I am some reference I will add. If you go through this reference, then definitely you get to know about the theory behind this formulation. Okay. But at present what we do is how this theory, I do not say discuss on how this theory works, but what is the final results and where we are going to proceed, that definitely we are going to discuss. Now, in case of a diffraction force, it is similar, that the 3-dimensional diffraction force here I can get if I know the 2-dimensional diffraction force. Okay. Now, here this H j x represent the 2-dimensional diffraction force, and now this is basically particularly for a section. Now, here if you remember we said that wave might comes for different angle, right. Now, diffraction force, the logic is this body is now here, the thing is that body is moving forward, it is not in a, it is not fixed, it is not for a 0 speed, remember that in case of a like added mass, we are considering the 0 speed and then we do the forward speed correction. Now, here suppose it is having diffraction force in a forward speed, then of course, we have this 3 dimensional thing. So, we have the encounter wave angle beta. So, therefore, at some particular section it is not simple x, it should be this one, right, because we have already know that just go back here, like if I do this. So, that is how actually we have defined this sectional fluid force, right, because it is if you remember our previous classes, we have discussed that it is now normally this phi I, the way we are writing is, or phi I or phi d, it is nothing but a g by omega into e to the power k z. Now, instead of sin k x minus omega t, we used to write as follows. We are writing this into sin into k x cos beta and then plus k x sin beta. Now, we have here this k x cos beta, and that is why you are having these things here. Anyways, and these terms again, as I said, this is again a forward speed correction. So, because of the forward speed it is coming, and really we are not going in detail into this theory how these terms comes actually here. So, if you follow this Fultinson paper, I mean STF paper, the classical STF paper, then all these discussions is there, but here our intention to how to get this sectional diffraction force. And after all applying all this theory, and we define now here this capital N is nothing but the 2 dimensional normal, and small n is actually 3 dimensional normal. So, n 1 equal to n 1, n 2, n 2, n 3, n 3, and then n 4 is nothing but the moment. So, it is, and then n 5 is again the in this r cross n the second term, and this is r cross n the third term. Now, how we can changes to the 2 dimensional strip, this is written over here. So, now the sectional diffraction force of any mode j, it can be defined as this expression. Now, how this comes, as I said, we do not discuss, but physically we can see some interesting fact is that you can see that my sectional diffraction force I represent as a sectional radiation force. Now, this is something very interesting, right. Now, you see there is a two different phenomena, is it not? One is that there is no waves, the still water, and then body start oscillating, and when they in case of a diffraction, we can say the body stands still and wave is hitting. Then how actually I can represent the radiation force, radiation potential to get the diffraction force. Now, the idea is like it is a matter of perception. Now, suppose if you think this way, now there is a wave is stand still and then the body actually pushing back, then it is a radiation force, right, is it not? Now, radiation force is water stands still and we just oscillate the body. Now, in diffraction this body is still and then wave is hitting. Now, instead of wave is hitting, if you consider some picture that wave is still and this body is pushing the wave, then actually we can say that okay, that could be some kind of a radiation component, right. So, so this is some very vague, I do not say vague, but very simplified physical understanding of this equation, and lot of mathematics involved here to do this, but we do not discuss that. But only thing is that why this is important, that this sectional added mass we can get through many ways, and maybe from the the next class onwards, we are going to see that how we can get the sectional added mass. Maybe today also in later part we are going to discuss that. So, thing is that we really do not have to find out the phi diffraction and phi radiation. If I get the phi radiation, using that phi radiation we can get the diffraction. Okay. Well, now let us take a special case. So, I take this beta equal to pi. So, then sin beta goes to 0 and then cos beta goes to minus 1. So, therefore, now this equation now I can see in this way, like that h d equal to omega 0 e to the power minus I k 0 x into I into n 3, because n 2 is having sin beta, so it goes to 0, and then this y 0 cos beta sin beta, that also goes to 0. So, this expression. So, now again from here we do not have to do anything. So, now in case of a heap, I just see that we have to solve for the phi 3, right, and then we have the multiplication of the n 3. So, now if I rearrange this further, so we can see that h 3 x equal to I into omega 0 e to the power minus I k x and then e to the power k z. Now, you see this is something actually very known to us. Now, if you look at this part, so this is the part actually we know for the radiation, it is very known for us, right. Now, suppose if okay, we know this result, of course. Now, you see from this result I know that n I phi 3, it is nothing but you can represent in terms of added mass and the damping. Now, you see this expression and this expression is very similar, only thing is that I have in integration e to the power k z. So, now if I do something, for example, if I try to approximate e to the power I k z, and if I replace by some constant value, then these terms also can go outside, and that only leads to omega square a I j minus I omega b I j equal to I can use this into this value. Now, you see the idea is here, that in this integration I need to do some kind of approximation to get this outside. Now, if I follow the STF paper, classical STF paper, they have written this expression as e to the power minus k dot d and dot s. Now, here this d is nothing but the sectional draft, and then s is nothing but the sectional area coefficient. So, d they are using at sectional draft, and then this s they using the sectional area coefficient. Okay. Now, so if I apply this, then this expression then I can rewrite as follows, it is nothing but I into omega 0 e to the power I into minus I into k 0 into x. Now, I have C 0 sorry, and also this now I can take out E minus k into d into s, and now I have over this C 0 n 3 into phi 3 into ds or dc, whatever, right. And then if I do that, then I can use this as a added mass and the damping, right. So, if we apply everything here, and then finally, we get as follows, we get the, now this is a very special case for head waves. If I try to figure out how to get the diffraction force, then this is the expression. And you know that this also it is very well known that beta equal to pi is the condition where we are interested to get all these wave loads, because it is assumed that when for the head waves it is much more dangerous compared to the other wave angle. So, in case of a sea keeping, if you try to figure out heap, pitch, coupling, etcetera, then beta equal to pi is the most crucial as I said, that most crucial heading angle, and then in that heading angle I can get this diffraction force is much more simpler way. Okay. Fine. Now, now let us jump into this. Now, you see that as you know, as you see here, that there is a lot of theory available and very complex theory to calculate the diffraction force, but however, the exciting force is much easier. Now, I would like to suggest you, not suggest you, like propose, this is not proposals, it is somehow like some simplistic way to calculate the exciting force. Now, suppose you are trying to get trying to write some code, sea keeping code using the strip theory, but you are you really do not know how to handle the diffraction force, right. So, I mean then suppose, but somehow as you know that the added mass and damping I discussed in very first class, it is available, the added mass and damping is available through some chart, and what is the chart, definitely I am going to discuss now. Now, suppose assume a situation, you know that added mass and damping these values, you have some chart of for this to get the added mass and damping of the ship, but you really have no clue how to get the exciting force. Then how you write the strip theory code? So, I just discuss it and then you try to write a strip theory code based on that. This chart for added mass and damping definitely can be provided, or it is available in internet. Now, how we do that as follows. Suppose if you have a ship and then now if is let us say the z equal to 0 line, and now if you superpose the wave here, no, it is not very bad way to superpose the wave. So, not like that. Okay, let us do it again. Yeah. Now, this is your z equal to 0 line, let us say, and then it is probably this is the superposition of the wave. Now, what one can do that, now they can take this extra buoyancy is the magnitude of the exciting force. Now, you know that the exciting, I mean the exciting force is a harmonic function. So, I can write that if the exciting force T equal to some magnitude into it is cos of omega t. This is how we write it, right. Now, we do not know that what is the magnitude or f 0. Now, what you can do that for in case of a heap, you can take this extra buoyancy force as a magnitude of the exciting force. Now, again if you know this magnitude, then if you take a moment. So, for the pitch now it is for the f 3, then for f 5 t you just need to take this m 0, which is nothing but if this is your the C g, then you have to take the moment about the C g to get the m 0, right, and then again it is cos of omega t. And now, you can see like how you incorporate the phase. Now, now if you for the low frequency limit is really work, because at that time there is no phase between the wave and the this wave and the response. So, therefore, you can take this phase is 0, and then very simplistic way you can calculate the exciting force in this expression, and then you can write a strip theory code. So, so the idea is you get this added mass A and B from the chart, and then you calculate this as a exciting force, and then you write the strip theory code. So, this will get from the chart, this is available for you, and then you are ready to write the strip theory code. Okay. Now, let us discuss that what actually you are trying to figure out, like before that before we go to the radiation force, let us discuss about the restoring force also. Now, in case of a strip theory, it is same, is a geometric property, and this is how we can get the restoring force. So, therefore, there is no big deal, we know how to get it. So, we really do not discuss on this, because we have already discussed this for panel method, for Wamit type solution. So, only thing we would like to discuss as follows. Now, in case of a strip theory, what the data you are having is basically the sectional data. So, that is why how to get this coefficient, I just give some kind of a very quickly how to get this coefficient. Let us take heave or something else. Now, here what you are getting, the data set you are receiving is nothing but the in each section you are receiving the sectional sectional point, like sectional curve. So, maybe if you take this, then you will have a sectional curve like this, and let us say this is your z equal to 0 line. So, this is this curve you are getting. Then from this data, how you can get the this coefficient that like C33, C35 or C55. Now, it is very easy. Now, if you what you need to do is, at each section you need to collect these 2 points. At z equal to 0, what is your values? Now, if you plot this value, then you can get this shape that from the water plane area. So, it is at z equal to 0. So, now in z equal to 0 you have this curve, because this is nothing but you take this point in all sections, the y values at z equal to 0. So, if you make it, then definitely if you project that into this plane, you are getting these values. So, you have this value. Now, if you integrate it, then if you integrate it, you get the water plane area, right. If you integrate x into b into d xi along L. So, it is nothing but your moment about the water plane area. So, therefore, your C35 equal, you can get about this minus rho g into this MWP, and if you take the second moment, so you will get the C55 also, right. So, those things are very known to us, and so I mean we really do not discuss on this. This is very trivial, and at any point of time that you can use either trapezoidal rule or Simpson rule to get these coefficients, right. So, today we are going to stop here, and in the next class we are going to discuss on how we can get the 2-dimensional radiation potential, or maybe the 2-dimensional added mass damping, what are the methods are available. So, those discussion we are going to discuss in the next class. Okay. Till now, thank you.